All right, I'm gonna walk through a few things on this glider design, and just walk through some of the rationale here uh, behind this. And this is just one take at glider design. This is by no means a fantastic approach. It's just an approach to get you thinking about how things are related, and and what design variables you have, and how you might choose those design variables and what they'd be based off of. So we're going to start here with this baseline glider. This is the PDF that you have that outlines this glider. So we're going to consider a baseline glider with lifting surface properties as shown in table 2. So we've got 3 wings here. We've got a main wing, a horizontal stabilizer, a vertical stabilizer. The main wing's using a NACA 2412, has a semi-span of 4.5. And by the way, all of these are rectangular wings, okay, for this example. So it uses the full length of carbon tubing and a tungsten ballast at a 1/2 inch thick and 1.5 inch outer diameter. Okay, so these are the steps we're going to follow here. Design and static analysis, so we're going to go through here in this video. So we start off by making a copy of this mass and inertia calculation spreadsheet. You can click on that. It'll take you to a spreadsheet that you cannot edit, but you can make a copy of it. You just go up here and say File, Make a Copy, and that will copy it to your Google Drive, and then you can edit it there, okay? So we're going to save that to our own Google Drive and then compute the weight of each of the following. So we have all the information about this, for each of these components based off of this geometry here, as well as the information about the ballast and the carbon tubing. So all I've done here is entered that information. And so I'm going to kind of walk through this process. And for example, so all the green things here are editable. The gray ones are calculations that you can't touch. And then the peach color here are results that you might be interested in. And really what's most important is this section right here. In fact, I'm probably just going to change the color of that to highlighted in yellow. These are the things that I'm really going to care about at the end of the design of my glider, and I suppose we could add mass to that as well. So there's my total, and might as well make total. Okay, so those are things at the end of this glider I'm really going to care about. But right now we're just starting off. We're going to first, it says compute the weight of each of the following. So the main wing. Now this calculator is just making some estimates about this glider. To really get the weight of the main wing, if you knew the airfoil properties and the span and everything, you'd probably need to put this into some kind of a CAD package like CATIA or SolidWorks or Unigraphics or something like that. But these are just estimates, and we've got this thing called an airfoil volume ratio, and this is based off of the NACA 0012 series, so 2412, basically a 12% thick NACA airfoil. This is about the volume ratio of the volume that airfoil takes up within a rectangular tangle that goes to the max thickness of the airfoil and the max chord of the airfoil. So you basically draw a rectangle around this airfoil, and the airfoil itself takes up about 70% of that area. So this mass that we're going to compute is based off of that. Okay, it's just an estimate. It's going to get us close enough, at least for this project. Okay, so we've got a different line here for each of our lifting surfaces. So I just typed in main wing. I said this is on the left-hand side. And we have to do the left and the right-hand side separate. So it actually takes me 2 lines here to put the whole main wing in. It's got a mean chord of 0.75, a semi-span of 4.5 on each side, airfoil thickness of 12% or 0.12. And then the wing root location. In the instructions for this project, we're told to leave the main wing at the root of our coordinate system. So that's going to be a 0. And then here's some dihedral, but that doesn't matter. That's going to come in later. This is a later calculation. So we're going to start off with 0 degrees dihedral. In fact, I might as well just put that in here right now. Okay. But it doesn't affect our mass. So this is the mass in slugs. And so what I've done over here is, so after I downloaded this, I made a copy of this spreadsheet, I just added another tab here that's called glider calculations. And so I'm going to walk through and put all of the information from A1 here, and we'll go through each of these here. So I've already done this once, and I'm actually going to walk back through in this video and refine some of these numbers, but the thought process will all be here. So basically said, okay, this is equal to the value in the inertia calculator in H22. So I just said equals this guy right there. I could have copied this value in as well. But anyway, that times 32.174. 32.174 is an estimate for gravity. And so I need to take the mass times the gravity in order to get the force, the total force or the weight of that wing. And so these are the weights in pounds force. This is just mass times gravity of the main wing. Do the same thing for the horizontal stabilizer. So here's my H stab, put in the number for that. We've got a left and a right of 0.75, semi-span of 1 on each side there. Again, 12% thickness on the airfoil. The horizontal stabilizer is actually a 0012, so it's not cambered, but this airfoil volume ratio is pretty accurate, independent of camber, as long as you have a 12% thick airfoil. So anyway, so we got the 0.12 on those two, and then that gives a total mass of 0.001157. So that's what's being used here for the horizontal stabilizer. Actually, that's half of it. So we've got to do two of those, right? So we're taking H30 and H34 from the previous, from this other tab. Adding those together, that's the mass of the left and the right, and then multiplying by gravity. And then same thing with the vertical stabilizer. That one only has a single lifting surface, so there's V-stab. You have to choose left or right here, but it doesn't really matter. We're going to set this at 90-degree dihedral anyway. But anyway, put in the geometry there. It's also a symmetric airfoil 0012, 12% thickness, and then this is the mass of that. It's the same as one of the sides of the horizontal stabilizer, right? So that makes a lot of sense. So that's the vertical stabilizer. And so now the mass of the fuselage tube. This is the carbon tubing. So we've got a carbon fiber tube, and these are actually the first two things in this spreadsheet here. You've got the carbon fiber tube and the tungsten ballast, and we're told that we're going to use the full length of the tubing. We don't know where that's going to sit right there. That number, we're just going to start off at 0 for now, but we don't know really where that's going to be. But we've got 6 feet of tubing, and so that gives us a total mass of 0.006. So multiply that by gravity, and this is the weight we get, about 0.2 pounds. And then finally the ballast. This is the tungsten ballast. Again, we're told, now this is the length of that ballast. That's really the thickness of this cylinder. You know, how high is this cylinder? Well, we were told that it is a ½ inch thick. So this is a ½ inch, so 0.5 divided by 12, because this is in feet, right? And we were told that it was a ½ inch thick, so you got to take the 1/2 divided by 12 to get it into feet. So that's our length. And then we've got an outer diameter. Again, we don't know where where it's located yet, but we do know the outer diameter is 1.5 inches. So again, you take the 1.5 divided by 12, and that gives you the 0.125 there. So this is the mass of the tungsten ballast. It's got an inner diameter that we can't touch. That inner diameter is just big enough to slide on the outer diameter of the carbon fiber tube. So so those two are equal. And then this is our mass, the 0.014. So now that, so we take that over and multiply it by gravity, and we get 0.46 pounds. So we got about a ½ pound of ballast there. So then the total aircraft weight is just the summation of everything above that. So that's our total aircraft weight is about 1.1 pounds. Okay, so there we go. We've done A1. We've estimated the weight of the aircraft. A2, in your own spreadsheet, add equations to compute the following: the area of the main wing. Okay, so we've got a main wing semi-span, and I just typed these in here, so we know it's 4.5. We've got a chord of 0.75. It's a rectangular wing. So the area of the main wing is just the semi-span times the chord, and then times 2 of those, right? Because the 4.5 is just a semi-span. The whole wingspan is actually 9, so it would be 9 times 0.75, which is 6.75 here, that area. Okay, the aspect ratio of the main wing is just b squared over s. So I'm going to take the span, which is 2 times 4.5, so I've got 2 times b11 which is that 4.5. And I square that and divide it by the area, which I just previously computed there. So we get an aspect ratio of 12. All right. Atmospheric density at launch. Okay, so this density, I actually looked this up in a book, so that's where I found it. But you can also, there's this pretty slick calculator out here called the Atmospheric Properties Calculator. So we're saying that we're at an altitude of 5,000 feet. Let's see, we can choose our units over here. So we're going to leave that in feet. And then our velocity and reference length, those don't really matter right now. So these results require only the altitude. And the density here, you can see, is 0.020,484. That's in slugs per cubic foot. So that's off by 1 digit, I think, different than what I have from this book. In any case, I got 0.020,482. It has a 4 in the final place instead of a 2. Anyway, either way, that density is probably good enough for this estimate. Okay, and then what else does it say? Launch velocity if the glider is launched with a kinetic energy of 20 foot-pounds. Okay, so actually I've edited this. Let's put in the 20 there. So this is the kinetic energy. We've got 20 foot-pounds. And then what's the launch velocity? Well, the launch velocity was given to us up here, an equation for the launch velocity. It's equal to 2 times the kinetic energy times gravity over weight. Okay, so I've just typed that in here. And take the square root of that. So I've got the square root of 2 times B16. B16 is the kinetic energy times gravity, which is 32.174, divided by the weight, which is B8 there. Okay, and so that tells me that I'm going to be launching at about 34 feet per second if I use the whole 20 foot-pounds of force for launching. Okay, so that's my 34 pounds per second, and then, or feet per second. And then finally we're asked, what's the lift coefficient? If that's our velocity, what's the lift coefficient at launch? So we can take, that's just the weight divided by, so we're going to assume that lift is equal to weight, right? So we've got the weight of the aircraft here, B8, divided by 1/2 rho, which is our density, times the velocity squared, we're at 34 feet per second squared, times the wing area, which is 6.75. And I'm just referencing the cells that have that information in them, so I don't have to type them in. So anyway, so it says we're launching at a lift coefficient about 0.136. Okay, that's if we use the full kinetic energy here of 20 foot-pounds. Okay, so A3, in your own spreadsheet, add a computation to ensure the structural integrity of the main wing. Recall that the weight of the fuselage is a combination of the dowel and ballast weights. Okay, so for this we have to go back up and look at our equation for structural integrity. This is the equation that we're using, and this is just an estimate. We could talk about maybe a way to make this more accurate in the future, but basically the aspect ratio of the main wing has to be less than this value here for our wing to have enough strength that we don't stress it, so it doesn't snap during flight. So we need to compute everything on the right-hand side and just make sure that the aspect ratio that we have, which is a 12, is less than the aspect ratio that we get by computing all this stuff. So I've just typed in, I've called this aspect ratio max. This is the maximum aspect ratio we can have for the main wing. And I've just typed in this equation here. So this is 16 times Tmax over C. Tmax, that's the thickness of our airfoil, divided by chord. So that's a percentage. So ours is 0.12. We're using a 12% thick airfoil. Then sigma max is 7,200. That's given to us later in the project. Weight of the wing, W sub is B3. So I had computed the weight of the wing up here. So that's the 0.335. So that's right there, the B3. And then we're going to divide that by 21 times the weight of the fuselage. The weight of the fuselage, remember, is the weight of the fuselage is the fuselage weight, the dowel plus the ballast. So we've got to, so in here I'm using B6 plus B7. Those are my the weights of these two, fuselage and ballast. And then we've got to, let's see, times by B, which is 2 times the semi-span. So I'm using 2 times B11. This is the semi-span there. That's 4.5. So that'll give me a 9 right there when I do the 2 times that. and then times gamma, which is 0.804. That's another property of the foam. Okay, so I show that our maximum aspect ratio is about 46.5. So we're well beneath that, right? We're only got an aspect ratio of 12. So anyway, this glider is kind of under designed here. We could certainly increase the aspect ratio and get better endurances out of it. So we've got some wiggle room here. Okay, but that will come later, as we iterate on this design. This baseline design, we're not going to change that. We're just going to live with the aspect ratio of 12. And when you design your glider, you can then increase the aspect ratio as long as you make sure that your aspect ratio is less than this maximum aspect ratio that you compute for your properties of your aircraft. Okay, so A4, based on the estimate for the total weight of your aircraft, use what you know about the glide ratio to compute the velocity that will maximize the no-wind glide ratio for your glider. Assume an Oswald efficiency of 0.8 and a zero lift drag coefficient of 0.013. Compute the corresponding lift coefficient at that speed. This will be our design speed and design lift coefficient. Okay, so basically what A4 is asking us to do is look at some performance. If we know a weight of this aircraft is 1.1 and we know how much wing area we have, the ratio of those two is called our wing loading, and wing loading basically drives the optimum speeds that we want to be flying at. So I've added another performance tab here, and in this performance tab I'm just looking at some predictions for performance of this aircraft. Okay, so for this glider, this is the baseline glider. The total wingspan is 9, and I've just hard coded these in. So it's 9, weight of 1.1 pounds. The total wing area is 6.75, and the maximum lift coefficient, I guess we can estimate that's 1.4 right now. The air density, I've copied over my air density, aspect ratio of 12. And so the wing loading, the wing loading is simply the weight of the aircraft divided by the wing area. And so I've just computed that there, the 1.1 pounds divided by 6.75. This is really low wing loading, right? So 0.16 pounds per square foot. That's a pretty low wing loading. And so now we're saying assume an Oswald efficiency of 0.8 and a zero drag lift coefficient of 0.013. Compute the corresponding lift and coefficient at that speed. But what we want to find is the velocity that will maximize the no-wind glide ratio. Okay, so this is just an equation right out of the handbook, and you can find it in several textbooks. But basically, what I'm going to do is put in CD0 of 0.013 and CD1 of 0, and then an Oswald efficiency of 0.8 actually will give us, we've got to compute the CD2 off of that. I think I've got this right here for the project. If you use a CD0 of 0.013 and an Oswald efficiency of 0.8, let's see, this is the velocity that we would get. I forgot I need to kind of go backwards here to get the CD2. So let's see. Well, let's work off of this here. This is the exact same computations. I just don't have them quite labeled. This is the minimum drag velocity right here that we get out of that. So let me just copy that over and put it right there. So this is the minimum drag velocity. Okay. For an Oswald efficiency of 0.8, the 0.8 drives what I sometimes called CD2, and so that's probably I don't know, maybe a 0.03 here would give us 0.031, 0.032, 0.033. Okay, so that's about it. CD2 of about 0.033 gives us an Oswald efficiency of about 0.8. Okay, so I'm just plugging in 0.8. Doesn't matter. There's different ways you can type out this equation, either in terms of CD2 or the Oswald efficiency. But what I've done here is computed then the minimum drag velocity. So this is the velocity, and you can find this equation in the handbook. It's equation 715 in the handbook, or you can find it in Phillips's textbook. Anyway, this is just the velocity that is going to minimize the drag on the aircraft, and actually that's the the velocity that we want to be flying at to maximize our lift to drag ratio and our glide ratio in a no wind scenario. Okay, so we're estimating the no wind minimum drag velocity, and it comes out to be 15.94 feet per second. Okay, so and I've got plots over here where I'm plotting lift to drag ratio as a function of velocity, and drag here as a function of velocity. And anyway, you can see that those are being minimized right around 16 feet per second, or L over D is maximized right around 16 feet per second. And the glide ratio at that velocity is actually 24. Okay. Anyway, that's not the point of this video. Hopefully you have some understanding of this performance calculation, and we're just using it as kind of a quick estimate to see what velocity we actually want to be flying at. So I'm going to say it's around 16 feet per second, right? That's what I want to be flying at. Now if I launch with my full kinetic energy here, I'm going to launch at 34 feet per second. So maybe I don't want to do that. We'll come back and revisit that later, but right now I want to design this glider based just off of its weight and wing area. These two things here tell me that, and an estimate for the Oswald efficiency basically, and a drag coefficient, say that I want to be somewhere around 16 feet per second. And we're going to come back and refine this later if you want to, as part of your glider. You can come back and refine this to get a better, to just refine the design of your glider. But we're just going to work through this with this design speed of 16 feet per second. So then what's our lift coefficient? If we're flying at 16 feet per second instead of 34 feet per second, what's our lift coefficient? Well, it's the exact same math that we did up here for this lift coefficient. We just use this with a different velocity. Use the same equation but swap out the velocity, and we get a lift coefficient of about 0.622. Okay, so that's my design lift coefficient. So I'm going to design this glider to basically be at a lift coefficient of 0.622, because if it's designed there and trimmed at that lift coefficient, then it will force it to fly basically at this design velocity of 16 feet per second at the altitude and in these conditions that we're looking at. Okay, so that's that was A4. Okay, so A5 says create the main wing using mockup 4, including the section airfoil information. Okay, so we're ready to use mockup. So you can go to aero.go.usu.edu/mu4 and add a wing in here. So there's my main wing, and now we want to go into geometry of that main wing and change it. So we've got a semi-span of 4.5. I'm going to do this rather quickly. There's a lot of options in here that you can play around with, but I'm just going to be going through the basics here. So we're using a NACA 2412 on the main wing. That's the default when you add a wing in mockup, but we have different airfoil properties than what are defaulted in mockup. So here's our airfoil properties that we were given here. For the 2412, we've got a minus 0.0455 for the zero lift angle of attack in radians. For the lift slope, we have 5.736. For the next one, we've got minus 0.0388. Then we've got minus 0.08, that's correct. And then we've got, for the drags, we've got 3 drag terms here. The first one is 0064. We've got minus 0.0021, and then 0.0062. Okay, so now I've got the airfoil properties of my wing set, and this is going to be I've set these properties for the root airfoil, and for the tip airfoil we're going to say it's the same as the root. If we don't have that selected, we could put a different airfoil here out at the tip, and it would linearly interpolate, from the root out to the tip for the airfoil properties, but it's the same here. We're using a 2412 all the way across. Okay, so at this point we have our wing built in mockup, at least everything that we know about this wing, including the geometry and the airfoil. And now let's move on to A6 here and talk about mounting angle of the main wing. So this says to maximize efficiency, we wish to mount this wing relative to the fuselage so that it provides all the lift at the trim condition and requires no lift on the horizontal stabilizer to trim the aircraft. Using mockup 4, find the mounting angle of the main wing such that the main wing will be at the design lift coefficient with 0 degrees angle of attack. You may find the target CL command to be useful in this process. Okay, so eventually we're going to have a fuselage in here running along the x-axis, and usually you minimize drag on a fuselage by having it at a really low angle of attack, and so and 0 if possible. And so we're going to design this particular glider so that it flies at 0 degrees angle of attack. And you can, when you're running this, you just put in, that's alpha, that's the angle of attack, just put in a 0 there. And so let's just update results right now. We've got a reference area of 9. Now that doesn't seem quite right. Oh, one last thing that we forgot to do is the chord. So we're doing a Hershey bar wing here, and these, the chord, the root and the tip are 0.75. Okay, so that was the last component I guess we forgot to do on the design of the wing in mockup. So anyway, run this at 0 degrees angle of attack. I'm just going to click on update results, and it says you have a reference area of 6.75. So that's the area of the main wing that it's computed, and it knows what that is because we have this main wing checkbox selected here for wing 1. And so anyway, it's adding up the area of that wing and using that as a reference area. From that, it's also computing the longitudinal length and the lateral length. These are just things for non-dimensionalizing these coefficients down here. And it says at 0 degrees angle of attack, we're going to produce a lift coefficient of 0.2188. Well, back here in our design spreadsheet, we were saying that we want to design this to be at a lift coefficient of 0.622. So, so that means that we need to increase the mounting angle here. This needs to be at a higher angle of attack because lift goes up with angle of attack. So we need to increase the mounting angle of the main wing. So how much do we need to increase it? And we could play with it, right? So the mounting angle right now is 0. And let me just show you how this works. If I put in a 10 there, you see that it rotates it by 10 degrees. So now it's mounted relative to that horizontal x-axis by, it's rotated up 10 degrees. So let's run this and see how we're doing here. So up at 10 degrees, we're at 1.06, lift coefficient of 1.06. Well, that's too much, right? We need to be at 0.62. And so we could iterate on that until we got the mounting angle just right. Another way to do that, though, is I'm going to set this mounting angle to 0. And on the analysis tab, I'm going to instead run something called target CL. And that's where it says down here in these instructions, you may find that the target CL run command will be useful. So what's going to happen is I've set this at a 0 degree mounting angle, and by running target CL, mockup is going to basically increase the angle of attack of the entire aircraft until it hits a lift coefficient of my choice. And in this case, we want to be at 0.622. And so now I'm going to update results, and it's going to take just a second, iterate through, and it says you need to be at an angle of 4.8 degrees. You're in, this whole system, and right now we just have a main wing, but if you had an entire aircraft in here, it'd be saying the angle that you need to be at is 4.8 degrees in order to get a lift coefficient of 0.622. And after it computed this, it automatically autofilled that angle of attack in case we'd like to do some analysis at that angle of attack. Well, we actually don't want to do any analysis at that angle of attack, so I'm going to put that back to 0. But I'm going to use this 4.8 and change that to be the mounting angle of the main wing. So I'm going to rotate that by 4.8 degrees because that's what it said was the angle of attack needed to produce that lift coefficient. So now that's mounted at 4.8, and instead of running target CL, I'm going to go back to forces and moments, update results at 0 degrees angle of attack, and there we are. We're at a lift coefficient of 0.622. Okay, so that gives me a mounting angle here for A6 of 4.8. All right, so that's A6. All right, so A7, in order for the aircraft to be trim using only the lift on the main wing, excuse me, the wing must be placed relative to the center of gravity such that there is 0 pitching moment about the center of gravity. Okay, so let's come back over here to components. We have this center of gravity component, and when you click on it, it highlights it with the arrows here, and we can move that around. We can say, yeah, I'm going to have my center of gravity be clear back here, and later we can move that by moving the ballast around on the aircraft, So this is our center of gravity, and really we can choose any location for that center of gravity at this point in the design process. But I'm going to set it back to 0 for just a minute and see what happens on my forces and moments. Now, I don't need to actually update these because these were run with I'll just run it anyway. Okay, update results. We're at a lift coefficient of 0.62. This is our drag coefficient. We have a 0 rolling moment, 0 side force, and 0 yawing moment, and that's because we have a perfectly symmetric aircraft. We don't have any side slip right now, so those are all 0. But notice we have a pitching moment. Now, all of these forces and moments are taken about the center of gravity, and so you can see that we have a nose down. This is a negative pitching moment. So based off of the location of the wing right now, it's going to want to nose down. The airplane is not in a trim condition. In order to be in a trim condition, this pitching moment also needs to be 0. And so basically what we need to do now is, so we're at minus 0.475, and you can think through the math on this to recognize that because this is negative, we actually need to move our pitching moment, or our center of gravity back a little bit. And so let's update results there. And now I'm positive 0.1695. So we can iterate on this until we get till we get 0 pitching moment. And you know, dragging this is not super accurate, but it'll get us really close. Okay, there I've flipped signs, so I need to come back just a little bit. Okay, so we're getting really close now. To be a little bit more accurate, you could actually play with the numbers here. This is the position of the center of gravity, and so, you know, when you're dragging this, you only have so much control over exactly what's happening, but you can play with the numbers there until you get 0. So I think the number is close to minus 0.0569. Let's see if that works. Okay, now that is really, really small, right? Very small pitching moment. So that's what I'm going to use for my center of gravity location. A little bit different than the last time I went through this, so I'm going to update that here, minus 0.0569. Okay, so if the center of gravity is at that location, then the aircraft will be producing a lift coefficient of this. That's based off the matting angle of the main wing, and we'll have basically a 0 pitching moment. Now that's not exactly 0, but it's really darn close, and of course we could keep iterating on that to get closer, but this is probably close enough for this point in the design process. And in reality, you're probably going to want to go through this process multiple times, refining numbers each time. As you know, once we get to the end of this design, we may not like some things about it and want to kind of iterate back through and make some changes. So for this, you know, this is the first cut through this design. That's probably plenty close. Okay, so that gives us gets us A7. So that's the center of gravity location. Oh, and then it says we're going to control the center of gravity location later in the design process by moving the tungsten ballast to the location that gives us our desired center of gravity. Using Mach 4, find the X location of the center of gravity, so the aircraft will be trim. Okay, actually, I guess we are done. We finished everything that it asked us to there. All right, so number 8, create the horizontal stabilizer using Mach 4, including the section airfoil information. Deselect main wing for the horizontal stabilizer surface, so its area is not included in your main wing reference area. Be sure the name for each lifting surface is unique. Place a horizontal stabilizer such that the glider has a static static margin of 20%. You may find the performance derivatives run command to be useful. Update the swing position in your mass spreadsheet. Okay, so we're ready to create a horizontal stabilizer now. So I'm gonna just click off of this here so that nothing is selected, and I'm gonna add a new wing. And this horizontal stabilizer probably wants to sit somewhere behind the main wing. And we have some information about this horizontal stabilizer. If we come back up, right here, it says that it has the horizontal stabilizer using a NACA 0012, has a semi-span of 1, and a mean chord of 0.75. Again, it's another Hershey bar wing. So let's go to components, and it automatically named this wing 2, but I'm gonna change the name of that to HSTAB. And then I'm going to come over here to analysis and into geometry, and we're going to set the semi-span to 1, and the root and tip chords to 0.75. Again, this is just a rectangular wing, and then the root airfoil, or the airfoil in general here, is a NACA 0012. So I'm putting in the 0012 there just so that it looks like a 0012. But then really the airfoil information is what gets fed in right here. So let's come back up here to where the airfoil information is given. So it's got a zero lift angle of attack of 0. That makes sense because it's a symmetric airfoil. It's got a lift slope of 6.118. Then we have a couple more zeros because it's a symmetric airfoil, and then 0.0058, a 0, and 0.0059. So I just pulled those numbers right off of here, okay, and then a maximum lift coefficient of 1.2. And then the tip airfoil is the same as the root airfoil. It's NACA 0012 all the way across. Okay, now we've got to deselect main wing right here because right now it's saying, yes, I'm going to include this area in the main wing area. We don't want that to happen, so we're going to deselect that. And so now it's not going to include this area when it computes the area for, to non-dimensionalize all the coefficients. All right, so we've created the geometry, and now let's see. It says create the horizontal stabilizer. Be sure the name for each lifting surface is unique. So we've done that. Place the horizontal stabilizer such that the glider has a static margin of 20%. And you might want to use the performance derivatives. Okay, so let's come back over here to analysis. We want to be running this at 0 degrees angle of attack. That's where we're designing this to fly at 0 degrees angle of attack for the entire aircraft. Remember, we rotated our main wing up, so it's creating enough lift at 0 degrees angle of attack. Okay, so let's just update results here. You can see that, yeah, the fact that we have a horizontal stabilizer there is going to change our lift coefficient. It's also going to change our pitching moment, and we'll come back and fix that later. But right now we're trying to find the position, and we're going to use performance derivatives to do that. So if I run performance derivatives and update results, okay, so at the bottom of this list of performance derivatives, and it's got derivatives with respect to alpha and beta. At the bottom is a static margin. So right now we're at 28% or 29% static margin. So that's a little bit much. We've got a little bit too much pitch stability. So I'm going to scooch this forward just a little bit, update results. And what we want to get this down is to a 0.20, 20% static margin. Okay, we're at 21. So we're getting real close. And there we go, 20.29, so still a little high. And again, I can fine tune this by going over to the location of the horizontal stabilizer here, the object, and changing this number by hand. Let's just try to get this a little bit closer. So we're at 19, so we need a little bit more, so I need to slide it back just a little bit. Okay, that's really close, 20%. So that gives me a location now of minus 1.9492 is the number there. Okay, so that's my horizontal stab location. And if it's that, if I put it right there, then that will give me a static margin of 20%. Okay, so that takes us through A8. So A9 says create the vertical stabilizer now using Mach-up 4, including the section airflow information. If your vertical stabilizer is set to both, the solver will hang and not be able to produce a solution. So let's go to that. So I've deselected everything here. I'm going to add another wing, and we're going to have that vertical stabilizer sitting somewhere back here. Let's go in and change its name to VSTAB. And then the geometry, it also has a semi-span of 1 and a root and tip chord of 0.75. So it's also a rectangle. And let's just fill in the airfoil information here real quick. So NACA 2412, it's really a 0012. And let's come back up here to our airfoil information and type that in. So we've got 0, 6.118. 0.0058, 0.0059, and 1.2. Okay. And the tip is the same as the root. Okay, so we've got the airfoil information in there. And so now, and we want to deselect the main wing because we don't want to use that area when we compute our reference area. So the way that we create a vertical stabilizer here is by changing the dihedral. So I'm just going to change this actually to about 80 degrees here so you can see what this looks like. So what it has here is two surfaces. You've got a left and a right that have been now rotated up to 80 degrees. So that's our vertical stabilizer. What we really want though is, so if we go to 90 degrees, it will have two surfaces there that are actually overlapping, and we don't want that. That will cause numerical issues when it's trying to solve the aerodynamics. So really what we want is just a left or a right. It actually doesn't matter which one. So I'm just going to use the right one and put it at 90 degrees. And because we have a symmetric airfoil, it doesn't matter if I chose the left or the right. This has the same airfoil properties because it's symmetric, whether it's left or right. So, I could change that to the other one and it wouldn't matter here. So anyway, that's how we create a vertical stabilizer. So now we've got the geometry in there, and it asks us to place this. Let's see, A9, deselect the main wing. We did that. Be sure the name is unique. Okay, place the vertical stabilizer such that the glider has a yaw stability derivative, Cn beta, of 0.1. Okay, so again, I'm going to come to analysis, performance derivatives, update results, and double check that my reference area is not changed. So that reference area is still 6.75, so that's good. That's the area of the main wing. And then Cn beta right here needs to be 0.1. So we look for Cn beta, and right now it's 0.06. So we need a little bit more yaw stability. The way we get more yaw stability is we move this further back. And we'll update it again. So 0.07. Okay, so we're getting close here. 0.08. And 0.09. You could do this a little bit more methodically, actually track in a spreadsheet what your location is and what the yaw stability is, and then draw a line through that, or plot that with a line through it, and then very quickly iterate in on what the location needs to be. But okay, we're at 0988. That's real close. Let's see if we can bump it up just a little bit more to get to 0.1. And again, it's not really imperative. Oh wow, we were really close there. I'm going to call that good enough. It's not really imperative that we hit this exactly. These are just some starting numbers, and later in the design process, you're going to want to go back and change things about your glider anyway. So anyway, this is just kind of getting us close enough right now. So let's go back to components and find out where that main wing is. It's at minus 3.3415. Okay, so about the same as what I had before. Minus 3.34 is the vertical stab X location. Okay, so that's A9. So A10 says add dihedral to the main wing until the glider has a roll stability derivative of CL beta of minus 0.15. Okay, this is higher than most aircraft, but we wish our aircraft to be very stable in roll to avoid a spiral mode. Update the swing information in your mass spreadsheet. Okay, so let's add some dihedral here. So on the main wing. So first of all, let's come over here to our CL beta. That's our roll stability derivative. It tells us how much stability we have about the roll axis. And right now we're at 0.0285. So actually that's not even the right sign that we want. We've got a positive roll stability derivative. We really want a negative one. And the way you increase roll stability is you increase the dihedral in the main wing. So I'm going to go up to 5 degrees dihedral. And let's update the results here. Performance derivatives. And I'm looking for CL beta. Now I'm at minus 0.0596 instead of a positive, I can't remember what the number was. We want to get to a minus 0.15, so we need a little bit more dihedral here. So I'm just going to double it, say 10 degrees. Okay, and now we're real close. We're at minus 0.1459. We need a little bit more. I think the number I had before was 10.3. Let's try that and see where that gets us. Minus 1511. Okay, so a little much. So let's try 10.2. Okay, so that's real close. So I'm going to say that we need 10.2 degrees of dihedral here. So 10.2 is for A10 there. Now it's important to understand that everything, all these lifting surfaces are working together. And so, the vertical tail, for example, is providing some roll stability, or it's changing CL beta, even though we designed it mostly for CN beta. Notice that as we added dihedral in the wing, now our CN beta isn't exactly 0.1. Remember, we designed it to be 0.1. We put the vertical tail at a location that would give us 0.1 here. Well, now it's off a little bit because we've added dihedral in the wing. So all of these things affect each other. And what we've done here by walking through this process for sizing these things and getting this dihedral is we've been looking at the things that are most dominant. So, for example, CN beta, the vertical tail, is the most dominant design feature for controlling your yaw stability. The dihedral in the main wing is the most dominant feature for controlling roll stability. Your horizontal stabilizer is the most dominant feature for creating pitch stability or controlling pitch stability, or your static margin. Notice that our static margin has gone up, actually. So now we're at 25% static margin, and originally we designed it for 20% static margin. Well, that's because the dihedral is played into this, the vertical tail is played into this. These things are all interactive, and so our stability parameters here change, and so if we want to get the static margin back though to 20%, I would be playing with the location of the horizontal stabilizer now to get that back, because again, it's the most dominant feature, even though these other components affect it. Okay, so so we have our we've got our dihedral figured out here, and then it says update this wing information in your mass spreadsheet. And actually, it's been asking us to do that for each of these last few steps, and I've forgotten to do that. So let's come over here to our inertial calculator, and basically what we need to do now is update the H-stab and the V-stab information, and the main wing here, I guess, as well, to capture what we've done here in mockup, so we can predict the mass properties of this. Okay, so let's start with the main wing. The only thing that we changed on the main wing is the dihedral. So that's now at 10.2 degrees for both the left and the right. Okay, so that's going to rotate the wing here, and it doesn't change the mass of the aircraft, but later it does affect the CG location, and it also affects our inertia tensor over here. Okay. Okay, the horizontal stabilizer. Let's find out where that is sitting. So our H-stab is sitting at minus 1.9492. Okay, so I need to put in minus 1.9492 right there. And remember, this is all in feet. I'm using feet for everything over here. Now, Mockup 4 is completely non-dimensional, so you can be using any units that you want as long as you're consistent between everything. So I'm using feet for everything over here, and that's what we're asked to put in this spreadsheet here. So let me copy that down here, minus 1.9492. That gives us that location, and it doesn't have any dihedral, so that's 0. And then and these are just X locations. If I had a Y or a Z location, for example, maybe I want to design this to be a T-tail, so I'm going to move it up there. Then I would have a Z location that I'd be entering into this spreadsheet as well. But I don't. I just allowed these both, the horizontal and the vertical stabilizer, to be connected here to the X-axis. Okay, so that's the horizontal stabilizer. Now we go to the vertical stabilizer, and its location is minus 3.34. Yeah, that's close enough there. And it has 90 degrees of dihedral. So just make sure those are filled in correctly, and then that will give us now the CG location. You can see that it's offset in the Z direction here, because it's just half of a wing sticking up, and so the CG location is up. It's saying that it's 0.5 above the X-axis here. That's what that 0.5 is, and that's correct because we have a span of 1 here. Okay, so we've updated this stuff in the mass spreadsheet. All right, so now we're on to A11. Using mockup, find the mounting angle of the horizontal stabilizer such that the aircraft is trim in pitch at 0 degrees angle of attack. Okay, so we want to find the mounting angle of the horizontal stabilizer. So let's come back over here to our analysis and say we're at 0 degrees angle of attack. Let's just run forces and moments. and update results, and we can see that we're getting a lift coefficient of 0.59. Well, we really wanted 0.62, right? So our lift coefficient is a little bit low now at 0 degrees angle of attack, and that's because we've added some other things, added dihedral in the main wing. All these things, again, affect our lift coefficient, but not significantly, right? This is still pretty close to the 0.62 that we were designing it for. And we can also see that we're getting a pitching moment again. So remember, we moved to the center of gravity so that we didn't have any pitching moment with just the main wing. And this is, you know, all of these things just require iterative processes. You're going to want to go back and iterate on the design of your own glider. You're going to want to go back and refine these things. We're not going to worry about that, though. What we're going to do now is just take out the pitching moment here by changing the mounting angle of the horizontal stabilizer so that the pitching moment back at the center of gravity is 0 again, okay? And now you could actually move the center of gravity at this point to get rid of the pitching moment, or you can change the mounting angle of the horizontal. You could also do some things with the main wing to take out that pitching moment. But anyway, you know, it's a combination of all these things. I'm just choosing to only look at the mounting angle of the horizontal stabilizer at this point. But there are a lot of options, things that you could do here. So anyway, so let's just talk about how we would do that. Now, of course, we can go back to components and go to geometry and rotate, change the mounting angle here. So right now it's at 0 degrees angle of attack, and you know, we could change that to 5 degrees angle of attack and see what happens. So right now we're at 0.0768. See what happens, and now we're at minus 0.884. So actually, it was in the correct direction, right? Before we had a nose up pitching moment, because pitching moment was positive here. Now we have a nose down pitching moment. Pitching moment is negative, and we went about twice as far as we probably needed to. So you know, we could go back to you know, 2.5 here, and update the results and just continue to iterate on this, and that's pretty darn close. We could continue to iterate on this until we got the pitching moment to be exactly 0. But I'm going to show you one little trick here for finding this. So I'm going to go back to a mounting angle of 0 for the horizontal stabilizer, and I'm going to give it a control surface. Now, we aren't allowed to have control surfaces on this free flight glider in the final design. I'm just going to use a control surface to solve for the mounting angle here. So I'm going to say this has a control surface, and in fact it is a control surface. It is the elevator, and so it's going to go from 0, which is root to span ratio, all the way to a tip span ratio of 1. So it's the entire length of this wing here. So it goes from 0 to 1. And then the flap chord fraction at the root is 100%. The flap chord fraction at the tip is 100%. And I'm going to mix this with the elevator, okay? So when I change the angle of the elevator, basically it's going to use this entire thing as a control surface and rotate it. So now when I come back over here to analysis, I can use this number here instead. So first let's just update results, and we're going to see that we have this positive pitching moment again. And now if I set the elevator to 5 degrees, you can see that it rotates it by 5 degrees. And update results, and again we're getting the minus 0.861. So we're going through the exact same thing that we did before. I can go to 2.5 and update results. So you know, you're thinking, well, this isn't a big time saver, and that's right, because all I've changed is where I'm typing in this number now. Into this elevator box instead of to the mounting angle over here. But actually, we can go one step further. Let's go back to 0 degrees elevator, and I'm going to use something called pitch trim. And in pitch trim, we get to set a target lift coefficient, which it has from what we wanted before, and a target pitching moment coefficient, which is 0. So now what it's going to do is it's going to change the angle of attack and the mounting angle of the horizontal, it's going to change the elevator deflection, right? That's what it's going to use to pitch trim, but that's really tied to the mounting angle for us, how we've set this up. So when I run this, it's going to iterate on angle of attack and elevator deflection until we get a lift coefficient of 0.62 and a pitching moment of 0. Okay, so let's update results. Let that run here. and it says, okay, you need an angle of attack of minus 0.07 degrees. So we're off from 0 a little bit. We knew that because our lift coefficient wasn't quite the same, after we added in these other components. Our lift coefficient wasn't quite the same anymore, and so our mounting angle of the main wing is off just a little bit. We knew that, so we're going to get a non-zero angle of attack. But what it says is you need an elevator deflection of 2.35 degrees in order to trim this. Well, that is our mounting angle. Now again, because we ran this trim case, it automatically populated these numbers into angle of attack and elevator up here. We don't want that, so we're going to set those back to 0. And I'm going to use this 2.35 now to set the mounting angle of the horizontal tail, and I'm going to turn off the control surface and say it no longer has a control surface. It's just mounted at 2.35, and as just a check here, we'll come back to forces and moments, update results, and you see that we've got a really small pitching moment, so that's really close to 0, and our lift coefficient is also close to that 0.622 again, and we're at 0 degrees angle of attack and 0 elevator deflection. Okay, so, but these aren't exact, and you could go back and continue iterating on these, the mounting angle of the main wing, the mounting angle of the horizontal, and there's an infinite number of design possibilities here, and I'm just showing you one thought process, one way to look at this. Okay, so our mounting angle was 2.35, so let's come back over here and just fill that in. 2.35 for the horizontal stabilizer mounting angle. Okay, so that was A11. Okay, A12 says add the dowel as a cylinder to your model in mockup. Locate the dowel such that the aft end is coincident with the quarter chord of the lifting surface that is furthest aft. So update the location of the dowel in your math. Update the location of the dowel in your math spreadsheet. Okay, so we're going to add a dowel here. Well, mockup doesn't have a dowel exactly, but I can add a cylinder, and when that comes in, you can see it's in the wrong axis here. I want to rotate that around the z-axis by 90 degrees. Okay, so now it's at least pointed in the correct direction. And let's look at the size of this dowel. So let's see, let's come back up here to the instructions. Let's see, materials. So we've got 6 feet of carbon fiber tubing, which is 3/4 inch outer diameter and 9/16 inner diameter, attached to the fuselage. Okay, we're just going to worry about the outer diameter for looks here. So it's 3/4 inch, so 3/4, so it equals 0.75 divided by 12. I need that in feet, so that's 0.0625 feet. So let's go to the geometry here, and it's got a radius at the top and a radius at the bottom. That's in diameter, right? This is 3/4 inch diameter, so I need to divide that by 2 to get the radius. Okay, so the radius at the top is 0.03125, and the radius at the bottom is 0.03125, and the length here, let's see, the height, it called it, the height of the cylinder is 6 feet. Okay, so that's my carbon fiber tube, and I'm just gonna make it kind of charcoal color, just for looks here. So we've got a carbon fiber tube there, and so now this problem statement says, and in the rules we have to have all of our lifting surfaces connected to this, and so at a minimum, this tube has to reach to the quarter chord of that horizontal surface back there, the one that's furthest aft, so that I can connect it on there, right? So we can click on that and see where it is. It's at minus 3.3415. Well, since this tube is 6 feet long, if I offset it by 3.415, that will run that tip right to that point right there. So I'm gonna do that. So we want 3.415. So I'm gonna say it's at a position of minus 0.3415. Okay, so it slid it back so that the end of that carbon fiber tube is coming to the quarter chord of that vertical surface. All right. Now this is maybe a little sketchy. We probably, to have a real nice connection here, we probably actually want to run that further back, but According to the rules, we don't have to. We can just run it to the quarter cord and say that that's enough connection here to mount this and glue it on, so it's going to be, going to be a tight fit. And the reason that we want this further forward actually is because usually you need more weight in the front to get your center of gravity correct. And so you can see we've got a whole lot of space up here to put that dowel. We can slide it wherever we need to, and at the end of the day, we're probably going to want to cut off whatever length of this dowel we don't need, because it's just adding weight and drag, unnecessarily. Now, for this particular design, we're not going to worry about that, but again, that's something else you can iterate on. You can cut down your dowel so that you're only using it in the areas that you need, or at the length that you need to minimize drag and weight. Okay, so it said add the dowel, locate the dowel such that the aft end is coincident with the quarter cord of the lifting surface that is furthest aft. Update the location of the dowel in your mass spreadsheet. So I'm going to come over here. That dowel is at minus 0.34. That's correct, minus 0.3415. And then in the inertia, I'm going to come in here and say this is my carbon fiber tube. It's 6 feet, and the location is minus 0.3415. There's the outer diameter, inner diameter, anyway. And those I can't change, right? That was given to me, and so this tells me the total mass of that dowel there. And this is where the center of gravity location is. It's where the center of that dowel is, which is this point that we're entering right there. Okay, so we've put the dowel in. Okay, A13 now, it says use your mass spreadsheet, find the location of the ballast that results in the same X location for center of gravity computed in problem A7. Okay, so we wanted some center of gravity. Let's come back to our center of gravity here. We said that we wanted the center of gravity to be minus 0.0569, right? That's the X location of the center of gravity that we wanted. And so now we've got to figure out where to put this ballast so that is indeed the case. So it actually gives us a center of gravity of that location. Well, if I come over to my mass spreadsheet here, right now it says that I have a CG location. So up here, this is my total CG location. I've got a CG location of minus 0.355 X location. All right, so that's remember, X is positive out the nose, and so that's a ways back here somewhere is my center of gravity. So we want to figure out where to put this tungsten ballast so that the center of gravity is further forward. We want it to be at minus 0.0569. So the way we do that is just in this mass spreadsheet. Now I've got the location of all of my other things set here. So the main wing, here's the location of the main wing, the horizontal stabilizer, the vertical stabilizer, and even the carbon fiber tube. I've got that now. And based off of all this, and by the way, it has a tungsten ballast in here, and it's saying that it's sitting at 000. Based off of all this, this is the CG location. So what we want to do now is figure out what CG location of the tungsten ballast is going to give us the CG location that we want here of minus 0.0569. Okay, so I'm going to move it forward. Let's move it forward 1 foot. And actually that gives us too much, right? That's a positive 0.06. We want a negative 0.056. So let's do like 70% of that. Okay, so we're at minus 0.0631. So that's pretty close. We want to iterate on that maybe a little bit more. Minus 0.71. Let's see. 58. Let's go 0.72. 0.54. Okay, so it's somewhere between there. So let's do 0.715. 0.56. Okay, that is really close. I'm going to call that good enough. So this is minus 0.569, actually, if I round to this digit here, and that's what we were looking for over here. And again, how exact do you need to be? Well, you're going to iterate on this, and so as you get further through the design process, you want to be more and more exact, probably. So this is our tungsten ballast location is at 0.715. So I'm going to fill that in here. Our tungsten is 0.715. And let's see, what else does it say there? Find the location of the ballast that results in the same X location for the center of gravity in problem A7. Add the ballast to your model in mockup. From your mass spreadsheet, compute the final X, Y, and Z location for your center of gravity and enter that in your mockup model. Okay, so let's just do that first. So this is our final center of gravity location. So I'm actually just going to copy this, Control C, and come over here to my glider calculation spreadsheet. And I'm just going to paste the values. So this is my final center of gravity location for this glider. And I want to update that over here so that this center of gravity is correctly represented in mockup. So let's see, it's at minus 0.569. That's close enough there. For Y, I have 0. And then for for Z, I have minus 0.138. Okay, so my center of gravity sits up just a little bit. And I'm actually going to make that just a little bit smaller. I'm going to bring the radius down of that. Okay, so you can see where the center of gravity sits, and that kind of makes sense, right? Because we've got some mass above here, not only from the vertical tail, but also from the dihedral of the main wing. Got a fair amount of mass sitting above that, so we've got some Z offset for the center of gravity on this glider. Okay, so now we've got to add in our tungsten ballast. Again, this is just for visuals. The cylinder here and this tungsten ballast are not used in the aerodynamic calculations that mockup performs. Mockup only does aerodynamic calculations on the main wings, or excuse me, on any lifting surfaces. So these are just really for visual, for visualizations. So I'm going to add another cylinder in here, and again, it's going to come in the wrong axis. So let's see, we want to rotate this about the Z-axis by 90 degrees. And let's see, the size of that washer we were given up here. Let's see, it uses the full length of carbon tubing and a tungsten ballast that's a 1/2 inch thick. Okay, so a 1/2 inch is the height of this thing. So let's just do this again. So a 1/2 inch. I needed to convert that to feet. So equals 0.5 divided by 12. So 0.04167 is the height of this. So let's see, 0.04167. Okay, so that's the thickness of that ballast, and then we were told that it has a 1.5 inch outer diameter. So let's see, that's equals 1.5 divided by 12. So that's it in feet, and that's a diameter, but what we need is the radius here. So we need to take that and divide it by 2, and that gives us 0.0625. So that's the radius, 0.0625 for both of those. So both the top and the 0.0625 and the bottom. Okay, so there's the radius of that. And now the location. We said we need that tungsten ballast to sit at 0.715. So I'm going to come over here to the X location, 0.715. Okay, so there's my little tungsten ballast washer sitting out there. Anyway, so that looks pretty good. So that's the location. So we've updated that. So let's come back here to A13 and make sure we did everything. So I found the location of the ballast, add the ballast to mockup, and in the mass spreadsheet we computed the final X, Y, and Z location for the center of gravity, and we entered that back into the mockup model, and that's that red dot right there. That's our center of gravity location. Okay, use the drag approximations for cylinders given in D6, estimate delta CD naught for the dowel and ballast. Okay, so now we want to estimate how much drag is coming from the fuselage here. You know, from this dowel and the ballast here. Now, mockup, when it computes drag, and we can come over here and update results. So the drag coefficient here is the drag that's produced by all of the lifting surfaces, but that's neglecting the drag from these cylinders that we've added. So what we want to do is estimate the drag from those cylinders, okay? So let's come up to let's come up here and see what it says about drag on a cylinder. Okay, so drag of fuselage. The drag of the entire glider can be estimated by adding the drag from the lifting surfaces to estimates for the drag from the carbon fiber tubing and tungsten ballast. As an estimate in this project, we will assume that the drag from the tubing and ballast are independent and can each be estimated from known relations for drag on a closed cylinder with an axis aligned with the flow. Okay, so people have studied this for years. They know exactly how much drag is on a cylinder that's aligned with the flow. Okay, so we're going to treat these as two independent cylinders. We've got one long tube cylinder here. And by the way, we're going to assume that the ends of these are capped, right? So that no flow can go through the center of this. And so we're going to estimate the drag from the carbon fiber cylinder, and then we're going to estimate the drag from the tungsten ballast cylinder, and we're going to pretend like those are independent, like they were just sitting alone in the flow. This is how much drag they would be producing, and then we're going to add those together. Now, that's a little bit pessimistic, right? Because this guy, there's a few reasons this is a little pessimistic. It's going to give us higher drag than is probably realistic, and that's partially because this washer is sitting somewhat in the boundary layer that's building up along this cylinder. And we're saying that this is a closed tube, which, some flow could be going through that, lowering the drag a little bit. And we're actually double counting the area here on the surface of this tungsten washer. We're saying that that's a closed surface, and that it's also closed out here on the end of this tube. And so anyway, these things are a little bit pessimistic. So it's going to give us higher drag than we probably would have in an ideal scenario. But at the same time, we're neglecting other sources of drag from manufacturing this. We're saying that there's no interference, for example, in the connection here between the fuselage and the wings. How you've attached that glue and tape and whatever it is that's holding this all together. That we're completely neglecting those things, and so it kind of maybe comes out in the wash a little bit. So that's what we're going to do here, is just estimate the drag. So what we need to do is we need to know the frontal area. This is the frontal area. R is the radius of a cylinder, and then we've got pi, which is 3.14. So the frontal area is pi r squared. The surface area along the side of the cylinder, a sub s, is 2 pi times the radius times the length. Okay. Okay, so I've walked through this here. So here's the dowel. So we've got a radius here of 0.03125 in feet. We've got a length of 6 feet. And so the frontal area that I get is this right here, and the surface area is this. And all I've done is typed in these equations here, pi r squared, and then 2 pi r times L, okay? Okay, so then what we need to do is, I'm going to skip down here. What we're trying to figure out is delta CD naught of a cylinder. It's equal to 1.12 times the frontal area plus 1.15 times some friction factor times the surface area along the side of it divided by the area of the main wing. Okay, so that's what we're trying to get to. So this equation is actually pretty straightforward. The only thing that we need now is this C sub F. C sub F is a friction coefficient, skin friction coefficient, and we're going to assume a turbulent flow because we've got a blunt nose up front that's probably going to trip this flow to turbulent along the surface. And so here's an estimate for the friction along the surface of this cylinder as a function of what's called the Reynolds number, okay? The Reynolds number based on the length of the cylinder. So this is how we compute Reynolds number. It's the density of the fluid times the velocity times the length of that cylinder divided by the viscosity of the fluid, okay? So we actually have all of this information except for the viscosity of the fluid. And here's where I have the viscosity here. Now, by the way, again, where I get this is from this aerospaceweb.org. You can come down here. This is the dynamic viscosity, and we need it in, what are the units here? Slugs per foot second. Okay, so if I come here, slugs per foot second. So this is the dynamic viscosity, 3.6366 e to the minus 7 So that's what I've got here, 6366 e to the minus 7. It's kind of rounding in what it's showing here. But anyway, so that's my dynamic viscosity. And now I have everything that I need. I know the velocity. We're at 16 feet per second, right? That's where we're designing to up here. Now I know the length and the density. The density we had previously. Here's my density up here at the altitude that we're flying at. So anyway, based off of all of that, this is the Reynolds number that I get based off of the velocity and length of that cylinder. And then from that Reynolds number, I can now compute this friction factor, which is this natural log of 0.06 times the Reynolds number. We square that, and that's in the denominator. We have the 0.455 in the top. So this is my friction coefficient here, 0042. Okay, so this is for the dowel, and then what I get then that plugs into this delta CD naught for that cylinder, and that's just the 1.12, and I've just typed that in here, 1.12 times the area. So there's my A sub F there, plus 1.15 times the friction factor, which is this purple one, times the side surface area, 1.17 there. And then we're going to divide that all by the area of the main wing, which I have in B13 up here. The main wing area is 6.75. Okay, so when I do all of that, I get a delta CD naught of the dowel of 0.001355. And you can repeat that process for the ballast. So here's the radius and the length of the ballast, the frontal area, the surface area along the side, the Reynolds number, and the friction coefficient there. And then when we plug that in, we get a delta CD naught of the ballast, which is 0.002. So the total delta CD naught is 0.0034. Okay, so that's an estimate for how much drag, how much this drag coefficient, this is the drag coefficient over here, it needs to be increased by 0.00343 basically to capture the influence of those cylinders in the center. Okay, so that's part A14 there. So A14, we've now estimated delta CD naught for the dowel and the ballast. Okay, A15, for this finalized configuration, compute the following at 0 degrees angle of attack, the lift, the drag coefficient, remember to add the cylinder drag, and then these stability derivatives and the static margin. Okay, so I'm just going to fill out this information here for our final configuration. So I'm going to run this at 0 degrees angle of attack, forces and moments, update results, and so these are my final numbers here. So I get 0.6280, and then the drag, I actually get 0.0211, but I need to add to that the total CD naught from these two cylinders up here. So I've got the 0.0211 plus that, so that's my drag. CL alpha, let's see, I need to get that by running the performance derivatives. So we're going to update those. Okay, so I've got a CL alpha of 5.4780, CM alpha of minus 1.3102, CY beta of minus 0.3795, CL beta of minus 0.1423, and CN beta of 0.0856. Okay, and then it says my static margin is 0.2392, and I'm just going to check that. That should be equal to the negative of CM alpha divided by CL alpha. Okay, so yeah, 0.2392. Yep. Okay, so these are my, this is just the basic properties of this aircraft at 0 degrees angle of attack. All right. Okay, so that was A15. So A16, because the glider is stable in pitch, it will seek the angle of attack and velocity that satisfy trim. Assuming the glider flies at exactly 0 degrees angle of attack, estimate the zero wind glide ratio and distance this glider would travel starting from a height above ground of 50 feet. Okay, so at 0 degrees angle of attack, we know all of this information about the aircraft. And actually the glide ratio is simply the lift divided by the drag, okay? So I'm going to take the lift coefficient divided by the drag coefficient, and that's the same as the lift divided by the drag. So that's what I've got in here, that number divided by that number. And so I've got a glide ratio of 25.5. So basically, for every foot that I drop down in altitude, I'm going to move 25.5 feet forward, and that's what the glide ratio is. For every unit length that I'm dropping in altitude, then you multiply it by this glide ratio, and that's how far forward you're also traveling. So I'm basically traveling 25 times in the horizontal direction than I am in the vertical direction as I descend. And so if I start from 50 feet, then I can expect that it'd be the 50 times that glide ratio, and I'd end up gliding about 1,280 feet total distance before I hit the ground. And this is in a no wind scenario, right? If there's no wind out there, this is the glide ratio I'd have, and this is the total distance that I can expect to go. Okay, so that's A16. A17, use mockup to compute the lift and drag coefficients as a function of angle of attack from -5 to +5 degrees in increments of 5 degrees. Plot total drag coefficient, including the cylinder drag, as a function of lift coefficient. Compute the 3 drag coefficients, CD0, CD1, and CD2, and describe the drag of the entire aircraft as a function of lift in the equation this. Okay, so basically what we're doing now is, now that we have our entire aircraft designed, which looks like this, now we want to figure out what the drag polar looks like. Okay, and we've done this before on an airfoil. I've got multiple videos about that. We've talked about it before in class. But basically, for an airfoil, we can say that the lift and drag are related through a parabolic equation here. So the drag, if I had the lift, I compute the drag if I have these 3 coefficients, CD0, CD1, and CD2. These 3 coefficients basically define that drag polar in terms of a parabola, so that at any lift coefficient, I could predict what the drag coefficient would be. So that's what we're trying to do here is compute this, the 3 components of this drag polar are 3 drag variables now for the entire aircraft instead of just for an airfoil. Okay, so what we're going to do here is we're going to run mockup at 3 different angles of attack. So I've got -5, 0, and 5, and I'm going to pull off the lift coefficient and the drag coefficient at each of these for each of these scenarios. So I already have 0 actually. So 0. Let's see. Let's update results here. So our 0 is 0.6280, and then this drag actually is equal to this number right here. I had already run that at 0 degrees angle of attack, so I'm just pulling that number over here. And by the way, this was the drag. Remember, this was the drag coefficient plus the drag due to my cylinders up there. So that's the drag at 0 lift coefficient. So those are done. So now let's do -5 angle of attack, update results, and I get a lift coefficient of 0.1585. Okay, so 0.1585. And I get a drag coefficient of 0.0102 plus, so that's that number right there, 0.0102. And then again, I want to add in the CD0 here. So I've got the 0.0102 plus the CD0 from the cylinders, which is in B74. So that gives me that drag right there. And now let's run it at 5 degrees angle of attack and update those results. And at 5 degrees, oh wow, we get a lift coefficient. Well, let's put in the lift first here. So we get 1.1072 and a drag coefficient of 0.05 exactly, plus, so 0.05 plus again the cylinder drag, B74. Okay, so there we go. Now, one thing you probably notice here is that we're assuming that the cylinder drag is constant and independent of angle of attack. And, that's not really true. The cylinder drag will change with angle of attack, but this is our best estimate. Without running a bunch of wind tunnel tests or using CFD or something, this is a pretty decent estimate for that drag. And we're going to be flying at angles of attack very close to 0 because of the way that we're designing this aircraft, and so this drag coefficient should be decent. But there may be rules of thumb or relationships in other books, like Horner has a book about drag, and maybe in some other aircraft design books that are out there, there might be some better relationships for how that drag would change with angle of attack on these cylinders, but we're neglecting that, and it's good enough for what we're doing right now. Okay, so we've got lift and drag, and now I'm just going to plot that. In fact, let me just start this over, see how to do that. So if I just highlight these and insert a chart. Okay, so this shows CD, drag, as a function of lift here, and I like to put these because they're really data points. Let's see, we want to do not a line chart, we want to do a scatter chart. There we go. So we've got these 3 data points, boom, 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 and we've got lift on the x-axis and drag on the y-axis, and I'm going to click these guys. Let's see, we want to add a trend line. Okay, so we want to add a trend line, but we want that trend line to be a polynomial of order 2. Okay, so that's the second order polynomial. That's what this is, the second order polynomial. And we want to show, let's see, the label we want to be the equation. All right, so this is the equation that of a line, or of a parabola actually, that goes to these 3 points. And we needed to have at least 3 points to compute a parabola. So, and you could add more points to this. If you want to do every degree, do -4, -3, -2, -1, 1, 2, 3, 4 in here, and have a bunch of different data points in here. It'll still try to fit a parabola through all of that data. We're kind of doing the bare minimum here. We need at least 3 points, and so we've chosen the -5, 0, and 5 to try to capture what the drag is doing over this range. And now we're fitting this parabola to it. So this parabola here, actually these 3 values are the values of CD0, CD1, and CD2. So CD0 we see is 0.0138. So I'm going to type that in here, 0.0138. CD1 is minus, let's just type it in here, it's minus 0.00753. Notice that it's got the e to the -3 there, so that's why I've got 2 zeros in front of the 7. And then finally the x squared value, or the CL squared value here, is 0.0391. Okay, 0.0391. All right, so we got CD0, CD1, and CD2, and then it says, by the way, compute the Oswald efficiency for your aircraft from CD2. So Oswald efficiency is just kind of a measurement of how efficient we are relative to some ideal condition of an elliptic wing with elliptic lift distribution and all that. It's kind of the minimum drag solution that we could be at. And the way you compute that is you take this CD2 here, and the equation is actually 1 divided by pi times B14. Let's see, B14 is the aspect ratio. That's right. So it's pi times the aspect ratio in the denominator here, and then times that CD2 value, whatever we get for CD2, that all goes in the denominator, and then you have 1 divided by all of that. And that gives you this Oswald efficiency, and we see that we're at about 68%. Not fantastic. We could do better than that. And the way that we would increase that is actually by having a higher aspect ratio would help. Maybe lowering the drag a little bit. There's a lot of different things that could be done here to increase the Oswald efficiency, and actually in turn would increase the glide ratio. So let's just talk about a few of those ideas, for example, that might help. So this wing is really not optimized. We've just taken a rectangular wing and just run with it. And you may not want a rectangular wing. In fact, drag is reduced if you have a taper ratio of around 0.5 usually, or if you add some twist in the wing. So we could play with both of those. We could play with some washout in the main wing. We could play with taper ratio, tapering this down. and possibly increase the aspect ratio at the same time. And we have some room on the aspect ratio. Remember when we computed our maximum aspect ratio, we said, we can get up to 46. I mean, that's pretty big. So we have some room here to increase the aspect ratio if we want to, and play with the taper ratio and the twist, all in an attempt to lower the drag that is being generated by the main wing. So anyway, there's a whole lot of things that we could do here. We could also chop off this much of the dowel up here. That's creating some drag that we don't need. So we could cut it off, somewhere in here. And but that is helping with our center of gravity, so we might have to shift this washer forward, just a little bit to offset that. But still, we could get rid of some drag by chopping off this dowel. And anyway, there's a whole bunch of things that we could do here to increase the efficiency of this glider. So hopefully this is giving you some ideas, a place to start, and how to get going on this glider design. And this is just an example. These problems, so to speak, A1 through A17 here, are just they're just to get you thinking about what the different parameters are, what you might want to play with, just by walking through this example glider. Hopefully it's giving you some thoughts of what you can do with your own glider to increase the efficiency. And in a later point we'll get into the dynamics, because you're going to want to worry about Dutch roll or a spiral mode or a phugoid mode, things like that, and we'll get into that in just a little bit. Those can also really drive your design as well. So this is just kind of to get you started.